Our next example will be the other paradox of material implication. If A is false, then A implies B is true for whatever A is. So I've already set up a table here. We will start by copying this theorem that we want to prove into the bottom of our table. And now this is a conditional. So what we're going to want to do is prove this by conditional implication. So we will set up a new subderivation here that starts with the antecedent of the conditional, not A. This is an assumption for conditional introduction, and then it will end with the consequent of the conditional here. Then we can't work top down, not A. There's nothing we can do with that. So this is our new goal sentence. If A, then B. This is another conditional. So we're going to use conditional implication. So that's the rule we're going to use for it. That means we need a new subderivation that starts with the antecedent, which is A, and ends with the consequent, which is B. Let's write in these line numbers. Okay. Now, how are we going to get B? Well, notice what we have in the assumptions here. We assume not A here for conditional introduction, and then we assumed A for conditional introduction here. And those contradict each other, right? So we have contradictory assumptions. And remember what we said in an earlier video about the principle of explosion. If you have contradictory assumptions, you can derive anything you want. Our next goal sentence is B. So we can just derive B, right? All we need to do is we'll just use negation introduction. So we assume not B for negation introduction. And then all we have to do is we'll just reiterate A and not A into this subderivation. Oops, one. Oh, here we go. 1R. So we reiterate those into the subderivation. That is our contradiction. We don't need these rows, so I'm just going to delete them. That is our contradiction, which means that that allows us to derive B here by negation introduction. That's from lines 3 to 5. Then, having gotten B there, I'm just going to fill in all the line numbers and then I'll go back and do the scope lines. This subderivation here was lines 2 to 6. And then this here was lines 1 to 7. Let's set up these scope lines. So this derivation is complete. The principle of explosion is a really powerful tool, right? Once you end up with contradictory assumptions, then you're done, right? You just, whatever your goal sentence is, just assume the opposite of that and use negation introduction or negation elimination to derive it. And at that point, basically, you're finished. The key thing is, though, that it only works if the contradictory assumptions occur naturally in the course of working bottom up and setting the derivation up. You can't force it, right? It's not something that you can force. I mean, for an example of what I mean by forcing, look at this. Suppose you're trying to show that this is a theorem, A or not A. And suppose that you're thinking, well, the way that I'll derive this is I'll use the principle of explosion. So I'll start by assuming A, and then I'll assume not A, and then because I've got contradictory assumptions, then I'll assume the negation of this theorem, reiterate those in, and oh look, I proved it by negation elimination. We haven't derived anything here because this is inside two scope lines. So, like, this derivation has not accomplished anything at all, right? That line is buried within two scope lines. And I mean, there's no way that you're gonna be able to get rid of these. I mean, note that, when you make these assumptions, you don't get to make assumptions. I mean, when you make an assumption, you have to indicate the rule that you're going to use to get rid of the assumption. You can't just make assumptions because you'd like to use the principle of explosion at some point. That's not how SD works. So, I mean, this derivation here is just broken. Actually, this is one where you basically just have to start over and just scrap this whole thing and start from scratch.